All right, so now picking up with number 26. A spring of K value 600 is placed in a vertical position with its lower end supported by a horizontal surface. The upper end is depressed 20 centimeters and a 4-kilogram block is placed on the depressed spring. The system is then released from rest. How far above the point of release will the block rise? So again, with a spring, this is most commonly going to be a conservation of energy problem. And so we're going to start out here with a floor or whatever that it's sitting on. And we're told, and I don't have a good way to draw a spring here, so you're just going to have to bear with the fact that my spring is going to look a lot like just a straight line here. So my spring starts out like this, oriented vertically, and it has a box placed on top of it. And we're calling the position of this box, we're calling that height equals 0. But we're acknowledging that our spring at this point is compressed by a distance of 20 centimeters. So minus 0.2 for the position of the spring. And of course the box starts out from rest, so I'm just going to say the velocity at this point is 0. Now, what happens at the end? Well, the spring comes back to its relaxed position. So the spring is able to elongate again and no longer be compressed. And the box is able to sail off into the sky, and now the box is going to be way up here at some higher position. And so at this point, we know that we want to find the height. Try that again. We want to find the height. That's our unknown. We know that our spring is no longer compressed. And we know that, again, this object will once again come to rest at this highest position. So that's the basis we're going to be using for our conservation of energy equation. Remember that that's just going to be K plus U equals K plus U. In this case, we have both gravitational potential energy and spring potential energy. So we've got both of those terms in this equation. Now, initially, our height is 0 and our velocity is 0. So the only thing we have initially is spring potential energy. And that's 1/2 times K, which is given as 600, times x squared, which is 0.2 squared. And that's got to equal at the end. Well, again, at the end, the only thing we have is a height, so that's a gravitational potential energy. So that's going to be mgh. And the mass of this guy is 4. G is 9.8, and we want to solve for h. So now you should be able to just use your calculator to solve for h. Oops, that 1.2 is supposed to be a 1/2. I just saw that. Sorry about that, guys. So 1/2 times 600 times 0.2 squared, and then divided by 4 times 9.8 gives me 0.306 meters, which is answer D. And that was for problem 26. All right, 27. A constant force of 20 newtons is applied to an object of mass 8 at an angle 25 degrees with a horizontal. What is the work done by this force if the object causes a displacement 2 meters along the horizontal direction? Well, our equation for work is work equals force dotted with displacement. So dot D. What that means is force times distance in the same direction. So it could also be written as force times distance times cosine of the angle between them. All right, so in this case, the force is given as 20. The distance of travel is 2 meters, but the angle between the force and the displacement is 25 degrees. So if I plug that into my calculator, I got 36.25 joules, and that, oh, wrong problem, is answer C. All right, 28. An object with a mass of 10 kilos is moving along a horizontal surface. At a certain point, it has a speed of 16. If the coefficient of friction between the object and the surface is 0.4, how far will the object go before it comes to a rest? Use G equals 10 for this problem. So again, this one can be done either with forces and kinematics or with the work energy theorem. I'm going to choose to use the work energy theorem here to save time. And that tells us that the work done by friction has to equal the change in kinetic energy. And so in this case, the work done by friction is minus mu times the normal force, which is going to be mg, times the distance, and that's got to equal 1/2 mv squared. V squared minus 1/2 mv initial squared. Now again, our final velocity is 0, so that whole term there is going to go away. Oops, that's not what I meant. Try that again. That whole term there is going to go away because our final velocity is going to be 0. And we want to solve this for d. So I'm going to get that d is equal to, and the masses cancel out as well, I should mention. So v initial, which is, where is it? 16 squared, and then divided by 2 from the 1/2 times mu, which is, where did it go? 0.4, times g, which is 9.8. And when I plug that into my calculator, I get 32.65, which most closely resembles answer C. All right, 29. A 4-kilogram particle is moving horizontally with a speed of 5 when it strikes a vertical wall. The particle rebounds with a speed of 3. What is the magnitude of the impulse delivered to the particle? So our impulse is just defined as force times time, or momentum final minus momentum initial. In this case, since they told us all about the mass and velocity, it's just going to be mv final minus mv initial. So in this case, the mass is 4. The v final, because it rebounds, it's going to move back in the opposite direction. So I'm going to call that -3. And then minus the mass times the initial velocity, which is 5. And when I plug that into my calculator, 12 and 20 gives me 32. So the size of the impulse is 32 Newton seconds. So the answer is B. Notice that it asks for the magnitude there. We don't actually know whether it's in the positive or negative direction. That depends on which way you had the initial velocity going. So that's a little ambiguous. But the size is going to be 32 either way. 30. 2 ice skaters push off against each other starting from a stationary position. The 45-kilogram skater acquires a speed of 0.375. What speed does the 60-kilogram skater have? So this is an inverse collision. This is when they push off apart from each other, and collisions make me think momentum. So this is going to be a conservation of momentum problem. So m1v1 plus m2v2 equals m1v1 plus m2v2. So in this case, both of them are starting out at 0. Oops, that's not a 0. Both of them start out by not moving. But at the end, we have the 45-kilogram skater going at a speed of 0.375, and we have the 60-kilogram skater going at an unknown speed v. So now we should be able to solve for that velocity. 45 times 0.375 divided by 60 gives us negative 0.2813 meters per second. So the speed there is just 0.281, and that is answer B. So again, no negative there in the answer because it's not asking you for the velocity, it's only asking you for the speed. All right, next up is 31. At time equals 0, a wheel rotating about a fixed axis at a constant angular acceleration. I'm going to stop there. As soon as I read constant acceleration, that makes me think kinematics. This is angular, so this is going to be rotational kinematics. Has an angular velocity of 2 radians per second. 2 seconds later, it has turned through 5 complete revolutions. What is the angular acceleration of this wheel? So again, what do I know about the positions and whatnot? So theta naught, I'm going to call 0. Theta final, it tells us it goes through 5 complete revolutions. So 5 revolutions, but I don't want to leave it as revolutions. I want to convert that immediately into my appropriate units of radians. I do that by multiplying by 2 pi, so it's going to be 10 pi radians. My initial velocity is time equals 0, wheel rotating about a fixed axis, the constant angle has been angular velocity. Oh, has an angular velocity of 2 radians per second. I don't know about the final velocity. I know I want to find the acceleration. And we know that the time, oh, hold on, 2 seconds later it has turned through. Yeah, okay. The time is 2 seconds. So that's my setup. The thing I don't care about is final velocity. So that means I'm going to use I'm going to write it as x's just because I don't want to have to type out theta. So x minus x equals x naught plus v naught t plus 1/2 a t squared equation. And so if I plug this in, I get 31.4 equals 0 plus 2 times 2 plus 1/2 times a times 2 squared. And from that, I should be able to solve for a. So 31.4 minus 4 divided by 2. 13.7. And that appears to match up most closely with answer B. All right. There it goes. All right, so line there. Let's move on to 32. All right, a wheel rotating about a fixed axis has an angular position given by an equation. So this time I notice that there's a t cubed in there, which means this is not a constant accelerated problem. So this is not a kinematics. For this one, I'm going to have to use direct integration or some sort of calculus approach to solve this. The angle theta is measured in radians and t is in seconds. What is the angular acceleration of the wheel at time equals 2? So if I know the position as a function of time, I know the derivative of that is the velocity, and I know the second derivative of that is the acceleration. So my velocity is going to be the derivative of the expression. The derivative of 1 just gives me 0. The derivative of negative 0.3 t cubed is going to give me negative 0.3 times 3t squared. So that's just going to give me negative 0.9 t squared for my velocity function. And that means that my acceleration is going to be the derivative of that. So I'm going to get minus 0.9 times 2 times t. And so that gives me minus 1.8 t. Now they specifically ask us for the acceleration at time equals 2. So the acceleration at t equals 2 is just going to be equal to negative 1.8 times 2, which is negative 3.6 radians per second squared. And that most closely resembles answer D. All right, number 33. A 15-kilogram child is sitting on a playground teeter-totter 1.5 meters from the pivot point. What force applied 0.3 meters on the other side is needed to make the child lift off the ground? So seesaws, teeter-totters, those make me think of torque problems. This is a torque balancing to keep it from rotating type of thing. So we want the torque on the left to equal the torque on the right, or the positive torque to equal the negative torque, or the sum of all the torques to be 0, depending on how you want to phrase it. So on the left-hand side, or on one side, we have the force of m times g, and the distance, the r, of 1.5 meters from the pivot. And that's got to equal our torque on the other side. And the torque on the other side is the force times the distance, which they give us as 0.3. So when we use this to solve for force, it looks like it should be 5 times bigger, so something like, okay, so 15 times 9.8 times 5 should give us 735 newtons. And that is most close to answer B. All right, number 34. A 5-meter radius playground merry-go-round with a moment of inertia of 2,000 is rotating freely with an angular speed of 1. 2 people, each having mass of 60, are standing right outside the edge of the merry-go-round and step onto it with negligible speed. What is the angular speed of the merry-go-round right after 2 people have stepped on? So this is a collision or an interaction between the people and the merry-go-round. So this is going to be a conservation of momentum problem, but because it's a rotating system, we're going to use conservation of angular momentum. So I times omega plus I times omega equals I times omega plus I times omega. Now, in this case, the first object is the merry-go-round, and the merry-go-round has a shape that is a disk. So if we look up the moment of inertia of a disk, it's 1/2. Oh, actually, I take it back. We don't have to do this because they've given us the moment of inertia of the disk. But if they had given us the mass and the radius of the disk instead, you would put in 1/2 mr squared. But in this case, they just told us the moment of inertia is 2,000. Saved us some time. Okay, and they told us that the initial speed of the object is 1 radian per second. And then we have to add to that the moment of inertia of the people times their speed. But because they're not moving initially, it tells us that their motion is negligible to begin with. Their momentum is going to be 0 to start out with. Now, on the opposite side, at the end, we're still going to have the merry-go-round, which has the same moment of inertia. The merry-go-round has not changed shape. But now it's going to be going at a different speed, omega. And we have the 2 people. And the people, we don't know the shape of the people, so we're going to treat them like point-like objects, and their moment of inertia is going to be just mr squared. So there are 2 of them, and each of them have a mass of 60, and they're getting on to the outer edge of the merry-go-round, so their distance from the axis of rotation is 5. So that whole thing there, that's their moment of inertia. And then we still have to multiply that by their speed. Okay, so that's the equation we're looking at to solve for omega. And when I solve that for omega, it gives me 0.4. And what units was it in? Radians per second. And that looks like answer A. "35. At what height will the acceleration due to gravity of the Earth fall off to 1/2 the value it has at the surface?" So we learned that in universal gravity, the acceleration due to gravity is not always 9.8. Depending upon your location, it can be a different value. And so they want to know where would you have to be relative to the Earth in order for gravity to be 1/2 of 9.8. And so the equation here is that the mass times acceleration, our force, is going to be gmm over r squared. And that's going to be equal to our ma. So one of the masses cancels out. That's the mass of your object, whatever object you're dealing with. So, oops, that's not good to do. Let's cancel that mass out with that mass there. And now we want our acceleration to be 1/2 of the acceleration due to gravity. So 0.5 times 9.8 has to equal capital G, which is 6.67 e minus 11, times the mass of the Earth, which is 5.96 e24, divided by r squared. And so now we should be able to solve for r. So let's see. If we do that real quick, let's see what we get. 0.5 times 9.8 divided by 6.67 exponent negative 11 divided by 5.96 exponent 24, and then invert that, and then square root that. All right, so that gives me an R value of something like 9,007,162 meters. Now that's the radius, that's the distance from the center of the Earth. And they want to know what height above the surface of the Earth it will be. So from this value, we now need to subtract the radius of the Earth. And the radius of the Earth is 6.37 times 10 to the 6th meters. So if I subtract 6.37 exponent 6, did that really give me that? Nope, I typed that in wrong. Gosh darn it. Okay, 9,007,162 minus 6.37 E6. There we go. Gives me 263,7162 meters, which is 2.63 times 10 to the 36 meters, which most closely resembles answer A. All right. 36. In 1994, fragments of Comet Shoemaker-Levy 9 collided with Jupiter. Assume that these fragments came from an infinite distance away with zero initial speed and fell into Jupiter. What was their speed when they arrived at Jupiter's surface? Jupiter has a mass and a radius given. So if we want to find speed using universal gravity, remember that the big difference here is that universal gravity is not a constant force, which means we don't have a constant acceleration, which means we can't use kinematics to solve for the speed. To solve for the speed in space, you need to use conservation of energy. So this is a conservation of energy problem. So this is going to be k plus u equals k plus u. Now, initially, it tells us that we are infinitely far away from Jupiter. And that's telling us that our initial potential energy is zero, because for gravitational universal potential energy, we had that the gravitational potential energy was minus GMM over R. And we said that value is going to be zero when R equals infinity. So our initial potential energy is zero for that reason. Our initial kinetic energy is also zero because we're going to start this piece from infinitely far away, but also with a speed of zero. So both energies start out as zero. And then at the end, we're going to have 1/2 the mass of Jupiter times speed squared. Sorry, the mass of our comet squared. Try one more time. 1/2 times the mass of the comet times the speed of the comet squared. And then for our gravitational potential energy, it'll be minus capital G times the mass of Jupiter times the mass of our comet divided by their final distance between them. And so this is the equation that we want to solve for. What are we solving for? The speed, v. So if I solve this for v, I get v equals the square root of g times the mass of Jupiter times 2 all over r. The other mass, the mass of the comet, cancels out. So if I plug in square root of g, which is 6.67 times 10 to the minus 11, times the mass of Jupiter, which they've given us as 1.90 times 10 to the 27th, times 2, and then divided by the radius, which is 7.14 times 10 to the 7th meters, we should be able to get our answer. So square root of 6.67 exponent negative 11 times 2 times 1.9 exponent 27 divided by 7.14 exponent 7, close parentheses, equals. So for that, I got 59,580 meters per second, which looks most closely like answer D. All right. 37. The position of a mass that is oscillating on a spring is given by this equation. What is the period of this motion? So this is a simple harmonic oscillator. The general equation for a simple harmonic oscillator is x equals a cosine of omega t plus phi. That means that the amplitude of this guy is 12.4 centimeters, looking at the equation, and the omega value is 5.46. It is that omega value that is going to help us find the period of this motion. We know that omega is just equal to the distance divided by the time in angular measure, the angle divided by time. And so the angle is just 2 pi radians, and the time once around is just the period. So that will allow us to solve for the period. So the period in this case should be equal to 2 times pi divided by 5.46. And when I plug that in, that gives me 1.15 seconds as my period. And that looks like answer B. "38. A mass of 0.15 kilos is attached to a spring with a force constant of 3.58 and undergoes simple harmonic oscillations with amplitude 7.5. What is the total mechanical energy of the system?" So remember here that the total mechanical energy is conserved. So if you can find the energy at any position, you know the energy at all positions. The easiest position to find it at is at the maximum amplitude, because you know there that it's not moving. Its kinetic energy is 0. And so its energy is just going to be the spring energy, which is 1/2 times K, which in this case is 3.58, times the X value, the amplitude, which is 0.075 squared. And so if we plug that in, 0.5 times 3.58 times 0.075 squared, that gives me 0.010069, and that most closely resembles answer B. All right, 39. A car horn emits a frequency of 400 hertz. A car traveling at 20 meters per second sounds the horn as it goes away from a stationary pedestrian. What frequency does the pedestrian hear? The speed of sound in air is 343. So our source is moving away from our observer. This is a Doppler effect problem. So the Doppler effect says that the observed frequency is going to be equal to the source frequency times V minus V observed is on top. Oops, it's V plus or minus. How do I want to write that? Plus or minus V observed divided by V minus plus V source. I think that's the way I've given it to you guys. So in this case, they tell us that the source frequency is 400 hertz. This V is the speed of sound in air, which is 343. And then the observer in this case is not moving. That's the stationary pedestrian. So that's just going to be plus 0. And then we need to divide by the V again, which is 343. And now since the the source is moving away from the observer, for away we're going to choose the second sign, the lower sign, which in this case would be plus. And then the speed of the car is 20. So let's crunch that through our calculator. 400 times 343 divided by 343 plus 20 should give us 377.96. 377.96 hertz. And that most closely resembles answer A. All right, and that leaves us just one more. I think I'm going to pop it up here, so we'll put 40 over here where we have a little more space to work. A 10-year exposure to the sound of a riveting machine will cause your threshold of hearing to shift from 0 to 30. What is the sound intensity corresponding to 30 decibels? So they've given us the decibels, the beta, and they want us to find the intensity I. And we said there's only one equation in this whole semester that deals